next speaker is also the winner of the Korean Federation of Science and Technology Society Award, and Professor Juha from the National Nanyang Technological University. She is an assistant professor in the School of Chemical and Biomedical Engineering at NTU. Please welcome her.
Hi, good morning, everyone. I'm really honored to give this talk during this conference as one of the awardees. So today I try to introduce what I did so far at NTU once I moved to Singapore in 2016. So the title is the bio-inspired approaches to resolve existing issues in biofabrication. So before I talk about my I try to explain why I try to solve those problems through the bio-inspired approach. So by discipline, I study bio-inspiration through mechanical engineering and material science. And then through these two disciplines, I end up with bio-inspired structural materials and biomedical materials for tissue engineering. Those two are my key titles and the identities for my research. And then if you have those two backgrounds and then you want to work on biofabrication, then what you can do? That was my first question when I was at NTU. So my decision is then, yes, I know structure, and I know mechanics, and I know materials. And then when I try to take a look at the problems unresolved in bioengineering and biofabrication particularly, I found three interesting problems. The first is the cell viability issues in biofabrication. When you start dealing with the biofabrication, the cells are one of the key topics. And you realize that whenever you try for the first time, of course, the experts or researchers different, but if you start as a beginner, most of the time you kill the cell very, very easily. So the problem is that how we can minimize this kind of human errors and risk, and at the end, any potential toxic environment to the cells. So I want to solve this problem on more fundamental basis. So that was my first problem. And second problem is that there are many researches going on for the tissue regeneration and the artificial tissue. But one of the key problems is that vascularization. The problem for vascularization is that the vascular network in the human body is one of the key enablers that the living creatures to survive. They supply nutrients, gas, and remove waste. But for the biomimetic tissues, they don't have this kind of vascular network, so we cannot incorporate those functionalities into the artificial tissue system. Then how we can create the vascular network artificially within the tissue? There are many researches going on in that topic, but not many topics can deal with the 3D problems. They can do 2D vascular network using many high-end microfluidic techniques or the lithography, but they never do it 3D because it's more complicated. So I want to touch those 3D vascularization topic as one of my key problems at NTU. The third problem, maybe one of the professors today actually mentioned about the flexible electronics, but many people focus on development of device. But I'm more talking about the interface. If you want to make those devices usable, you need to think about how it can be used or implemented on human. Then how we can solve the interface problem. How you can, for example, even the simple medical bandage, when you apply to your wounded area, Do you think that your bandage can last long? You put it, and after 1 hour, you do some exercise, take shower, or just accidentally take off your clothes, then the shearing, the friction, or the humidity make your bandage better from your skin. Why we cannot deal with this problem so far? So those 3 problems, that was my key 3 problems which I want to solve while I'm studying here. And then I want to give you some my approaches which are not perfect, but just the starting point. Because as compared to other 2 great awardees in our talk today, my research career is still very short. So I cannot solve problem as delicate as they did, but you can see my efforts in some way. Okay. So this is what our research group so far doing, but I don't want to go through too much detail. This is the basically what we do. The first problem I touch, how we can handle the cells in biofabrication. So cells are very important in biomedical engineering. Should be one of the key enablers. The cell can be used for diagnosis. Cell can be used for your testing bed for the new developed drug, or biocompatibility for your materials, or sometimes even you use the cell for the therapy. But we don't really see how to make the cell survive in any cases. We only think about how cells respond to your materials, but how about their well-being? For example, how about their well-being? They sacrifice for you. Then how can you treat them well? So I try to think about when I try to share my experience when I started working on bioprinting. So I was very ambitious as a first year assistant professor at NTU. I started printing the cell using my new fancy bioprinter. 100% cell die, very efficiently. During 1 month, most cell die without any reason. I tried to use the very, very safe material. Even I tried to find one protocol that already proved very well. And I used all the materials that very, very safe for the cell. It won't kill the cell, but using my bioprinter, most cells efficiently die. I tried to figure out with my first PhD students to figure out why cells die. And then we realized that the cells actually undergo many, many toxic environments through the 3D printing system. First, during preparation of the materials with the cell, we stay too long. The cells cannot stay outside too long, but we didn't know that. Second, when you do 3D printing, a lot of techniques involved, especially to make the material from liquid to solid, because your material needs to be solid after printing, otherwise you cannot use it. Then during this solidification process, your cell also die because they're exposed to the UV damage or chemical toxicity, or sometimes the humidity or temperature changes. Because of that, as a result, you can kill the cell. Then, I don't know, because I need to move on my research. Because this is my first project, if I fail, I may cannot get the second project. So my decision is that, okay, I'm a structural engineer as well. So let's try to think about how to protect the cell. I don't know how to do it better. So instead, I start incorporating my idea into this problem. So I try to protect the cell instead of wish them survive through my oral biomedical processes. So I try to go to the nature because I'm bioinspiration expert. So I try to go to the seed coat because seed is very interesting system because it can make the cell inside survive. How? Because of those 3 mechanisms. They have the seed coat, and then the seed coat play 3 key roles. First, it can protect the cell through their barriers. They try to protect the internal cells through mechanical protection, chemical protection, and also gas barrier. So within this seed coat, the cell can be protected very well. Also, another strategy that the seed play is the dormancy. The cell is sleeping within the seed coat. According to the literature, there are 3 dormancy mechanisms induced within the seed coat. The first is the mechanical dormancy. Because the external layer constrains the internal layer, because of this induced stress, the cell, because of the enzyme, they actually fall asleep. The physical dormancy, they try to reduce the nutrients, and then for the protection mechanism of the cells, they induce some mechanism to make the cell sleep. The third one is a chemical dormancy. There's some enzyme or phenolic compounds actually make the cell sleep as well. There are 3 strategies that the seed coats play to make the cell sleep inside. But if you protect the cell and then make the cell sleep, that's good enough for the strategy. Why? Because eventually you need to use the cells for your research or for your application. Then how you can make the cell from the seed coat? The seed coat, the final fancy and most exciting mechanism, the failure mechanism. Once the time comes, the shell is broken. Then the internal cells release from the seed and then they can grow. So those 3 mechanisms actually in the nature already know how to solve the problem. Then why we don't use this strategy? But then the second problem to me is that, okay, then I may try to create the seed coat. Then how? That is the next problem that I need to think. So I focus on the polyphenols. Polyphenols is actually quite widely available and water-soluble compounds. They are short molecule, only the molecular weight of 500 to 4,000 Dalton, and then they usually consist of 12 phenolic hydroxy groups, and then also 5 to 7 aromatic rings per 1,000 Dalton. Then they are very interesting because they are well known to be antioxidants, the free radical scavengers, antifungal or antibacterial agents, and also growth inhibitor. So if we use these polyphenols as one of the chemical dormant components, cell dormancy components, and also try to use the UV protection agent because it can absorb the free radical, then we can maybe use the polyphenols as one of the candidate materials for the seed coat. And this seed inspired the cell-laden microparticles to the biofabrication process. And then after the time comes and then the cells are ready to grow, and then we try to break the microspheres and then make the cell grow. Maybe then we can increase the probability to make the cell survive. Of course, the result is good. That's why I'm here, is it? This is my second year research, and then I survived. That's why I'm here. So I published paper in that reasonably good journal, even though we still have a lot of remaining solutions. But basically, the cell successfully survived, but we still don't know why. But through the process, we try to compare those seed-inspired cell-laden microparticles with a non-protecting naked cell. And then most cases, surprisingly, cells survive regardless of any environmental condition. Even we are very excited because whenever when we use the seed-inspired cell-laden microparticles for any biofabrication process, their standard deviation quite small. That means that the sample-to-sample variation we can reduce as well. So quite interesting factor, but we still need to figure out why it happened and how we can improve the reproducibility and also how we can make this strategy for the large-scale fabrication. This is still remaining the issues that we need to resolve, but our first problem was successfully solved through one of the bio-inspired approach. Now, I wanna solve the, okay, seems something wrong. Okay, so now I wanna solve another problem besides the cell viability in biofabrication. Currently, many cells used through supply chain. When the cell produced from the cell factory, they deliver to the hospital for the doctors to use. There are some gaps between the production site and the consumption site. There's a transportation required. If you remember the Pfizer or the Moderna vaccine for the COVID-19, one of the issues is the cold chain. The Moderna, the vaccine, they require negative 20 degrees Celsius storage and transportation condition. Pfizer, negative 70. Can you build up this cold chain? It's very expensive. For the cells, the same. How you get the cell from the cell bank, and how you try to transport your cells from your lab to the hospital. This is not the easy problem because the cell need to be protected, but reasonably safe in terms of their logistics, but also need to be easily used, and also cell need to be survived through the process. So because of that, we try to think about the problem using the seed-inspired approach. So what we do is that we tackle the logistics issue for the cells, and then instead of using this cryopreservation, which costs a lot, require a lot of cold chain to make the cell frozen until you deliver the cells to the hospital, to the room temperature chain. Using this sporation approach, the cells are sleeping. Then, for example, when you try to go to the US from Singapore, if you imagine that you can take in the sleeping pill, you sleep when the flight is departure, and then when you arrive, your flight landed in US, you awake. Then how you feel? You feel very fresh because during the whole flight you can sleep. So same thing. If the cell sleep during the logistics, we can reduce the environment factors which influence the cell viability during the logistics. So what we want to do is that we try to develop those seed-inspired micro particles with the cells, and then try to implement this idea into the cell logistics, and then try to figure out how we can deliver cells in more cost-effective way, also minimal invasion, and then also with high cell viability. In conjunction with this strategy, we also want to develop the in situ monitoring method of the cells, because in addition to this delivery method, you also need to know that whether cells survive or not during the delivery. So we want to try to develop the in situ monitoring method of the cell viability during the transportation, also at the site that the cell delivered. So this is my first, approach, and then the problem that I want to propose. The the problem of the vascularization I skip because the time limit, and I jump to the part 3, how to improve the human device interface to make the flexible electronics more usable. The many flexible electronics, they're fancy, nice, very promising, I agree. But the flat geometry itself, as a structural mechanics experts, not a good idea. Your material is flat, you apply to the curved, especially intrinsically curved surface, always the mismatch between your geometry. The flat geometry never be conformed to your complicated curved surface. Why? Because intrinsically curved surface cannot be matched with the extrinsically curved surface. Then how we can solve the problem? Your material is very, very flexible, so the material become like a thin film and then avoid any bulk problem. Or your material has the same geometry that your substrate, your application. Then you can avoid this interface problem. So many materials have been developed for biomedical applications have the flat geometry. Because of it, you have many tactics and many problems happen. One of the examples is the facial mask. I mean, some ladies maybe have experience with the facial mask. Of course, the men, I don't have any gender discrimination. So the man or woman, whenever you guys have the experience with the facial mask, what you feel is that some area you never apply properly on your skin. Why? Because of interface. The material cannot deform on your surface. Why? Because of the geometry problem, structure issue. So our approach is that how we can develop the method to create the thin membrane which mimic your skin surface, the geometry problem, using the current 3D printing technology. But if you want to make the thin membrane using 3D printing, usually you need to go through multiple processes and it increase a lot of cost. And we want to have the direct 3D printing, which can mimic your surface very easily. So that's the first problem. So let's try to see how the people try to use the customized fabrication for the biomedical devices. So they use the CAD model after scanning your body, and then translation into 3D printing code, and 3D printed with the final product, we go through the post-processing. And then there are three common ways to produce the biomedical devices using 3D printing process. One is the SLA, stereolithography apparatus, and direct ink writing, and selective laser sintering. But in this way, since our ink is the silicone rubber for the flexible electronics, we try to use the thermally curable silicone resin, which are reasonably cheap and also widely used. But this thermally curable silicone resin, so far without any modification, you cannot use the 3D printing technology. So what we do is that we try to use the direct ink writing, DIW, for the printing system of this ink, but we need to make this ink printable using some tactics. So first, your ink needs to be rheologically well controlled to maintain their geometry after printing. The second, you need to avoid all the gravitation issues when after printing. Because of that, usually the printing is not a big issue. You can print the materials, but after printing, your material needs to maintain their shape. Otherwise, your printing fails. So how we can avoid this problem to make the successful 3D printing of the silicone rubber. So one of the methods that I focus on is the freeform 3D printing. The freeform 3D printing is the recently developed 3D printing method. We don't touch any hardware, but we try to design the 3D printing system with the soft materials to make the soft material printable. So what you do is that you try to create the supporting matrix set, and then you print the material within this supporting system. So the hydrogel microparticles should be one of the most popular way to produce this supporting matrix system. And then you try to print the material, your own material, into this hydrogel matrix to make the material printable. And then what happens is that your supporting matrix is viscoplastic. So at the beginning, without stress, they become like a solid. But when you try to make the printing nozzle move, the strain induced, the strain rate, depending on the strain rate, the yield stress actually achieved, then your matrix become liquid. And then allow the 3D printing nozzle can move within the matrix. Then you can print the material without any interference of the matrix. So this is the strategy that we did. So the silicone rubber membrane so far have been used using the indirect 3D printing method. So you try to print the mold using 3D printing technology, and then try to cast a thin film using this mold. And then you can get this silicone membrane. In this process, it's very straightforward, but the problem is that you need to produce the wasteful mold, and then you cannot customize the silicone rubber membrane easily because you produce the mold to make the customized silicone rubber depending on the individuals. So instead, we try to use the direct printing method using the supporting matrix system. So using this freeform 3D printing system, we can easily customize the silicone rubber membrane, and the silicone rubber itself also can be printed
without any gravitation issues. So we try to use the supporting matrix, which developed with arginate, because arginate is one of the biocompatible hydrogel materials, and also it's quite good, shows the good thermal stability. So we try to produce the silicon, the arginate matrix using the encapsulation process, and then we can control the rheological property depending on the particle size of the arginate. Also, there are individual stiffness of the particles. So we can control the rheological property depending on the condition that we produce using arginate slurry. And then we can also control the transparency of the matrix as well. So once we optimize the arginate matrix, we can also try to check whether our ink, silicon rubber ink, still okay to be cured within water. So what we do is that we try to print, we don't print, but we just briefly print the materials within the arginate slurry, and then compare with the casted silicon and then see is there any mechanical changes due to the arginate slurry. But we didn't see any clear interference in terms of their mechanical performance. The cured arginate, the silicon rubber specimen within arginate is actually same as the casted silicon rubber sample. So we conclude that we can use this method for the printing of the silicon rubber. And then this is the way we can do. So we try to choose one elbow system and then try to create the 3D geometry for this elbow model and then try to print within the slurry. Can show you how it works. So the silicon rubber ink actually directly printing within the arginate slurry. And then you see that even though the arginate slurry, actually, even though the silicon rubber printed within the arginate slurry, they can still maintain their position and then they don't collapse. So you can print this kind of complicated shape, and then you can control the porosity of the membrane depending on the structure design. Okay, and then one of the hypotheses for this project is that whether we can mimic the surface of the human body can improve the contact stability of the membrane system, even though your membrane is very, very flexible. So we try to demonstrate that the contact stability significantly improve if your material has the certain 3D conformal, the 3D geometric structure compared with the flat geometry. And then we do dynamic the elbow test, flexion and the extension test, multiple rounds. And then we found that if you have a 3D geometry for the flexible silicon membrane, it can maintain on the surface without any problem through the multiple the elbow motion. This is what we found. And then also for the economic point of view, if you use the slurry method, you need a large volume of arginate slurry for each printing. So if you only use the arginate slurry one time, it also increase a lot of cost. So we tried to check the recyclability of the arginate slurry. And then we found that even though we do multiple the printing round and the curing process, the arginate slurry can be used. And then if you want to recycle the slurry to maintain the quality of the printing, you can actually, this is our proposed recycling cycle to make the arginate slurry usable for multiple rounds. So this whole process only cost 30 to 40 bucks. A very cheap process, even though a little bit time consuming, but I'm sure that you can think of the mass production. If you do everything in parallel, then you can reduce the time. So I think that is very cost-effective method to print the silicon rubber so far. So this is our the proposed preform printing system besides this silicon rubber printing. So we can print the different the materials like PMMA or other the other materials which cannot be printable but used for the biomedical application. So we can introduce those materials into our preform 3D system and then print. If we can print the negative waves, then you can also print the 3D network within the matrix. You print the sacrificial ink and then create the 3D network and then try to cross-link the outside matrix and then remove the printed path, then you can create the 3D network. So this is one of the way we can create the 3D vascularization network. And then finally, you also can, because the good thing for ourselves is that you can print the materials within the liquid. So you can incorporate the chemical agent within the liquid, and you can also functionalize your material in situ while you're printing. So these three methods we can also work on now to make the biomaterials more functional and more applicable for the future application. So I acknowledge my lab, and I really appreciate. Without their help, I cannot come here. So I really appreciate their support and great work. And then we will continue to solve our problem. Even though I give you some example about how to solve the problem, but still there are many, many problems going on. So I will solve it, and then hopefully in the future I can give you better idea about how to solve those problems. Thank you very much.
Okay, so we do have some questions from online, and the first question is from Jay. What is the future of 3D tissue engineering, especially for 3D printing technologies?
The future of 3D tissue engineering definitely try to mimic the 3D artificial tissue, especially the large scale. Currently, many people start using the organoid as one of the 3D mimic structure, but I think that still the scale is issue. So I feel that in the future, the 3D tissue engineering with the 3D printing definitely try to make the artificial tissue with multi-materials and with more well-designed vascular network, and then make the system more usable, which can replace the animal test in the future. But that one is the really promising goal. So definitely there are still a lot of missing gaps. So we definitely tackle more problems to resolve this, the condition. But definitely I think that the future of the 3D printing, the tissue engineering definitely go for that direction. Artificial tissue with a reasonable and very well-designed vascular network, and then try to use it for various animal tests, which can save more animals in the future.
Thank you. So I think since we have a limited time, we will skip the next questions. Thank you, Professor Juha.